So, starting out with the last part of your topic number 4A, conduction in semiconductors. As we discussed, the main difference between normal conductors and semiconductors are that conductors have a lot of free delocalized electrons and they are better conductors. But semiconductors are even better conductors, but they have very small number of delocalized electrons as well, but they are free to conduct as well. For example, silicon, one of the most common elements on earth, and these free atoms have a series of discrete energy levels in which we can find their electrons. Energy level means different shells as well, depending on the energy the electron has received. If the electron receives enough energy, it will leave the atom altogether, leaving behind an ion. In solid materials, there are many atoms close together. The allowed energy levels become much wider, forming energy bands. अब different magnesium अगर एक metal है, it has 12 electrons. Each of the electron would have different energy. Some has this energy level, some of them might have this much energy levels, some of them might have this much energy levels. There are levels. We call these different energy levels at which electrons are actually present. The electrons can have
Right.
a large range of, yes.
No, 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 I just no.
So the electrons can have a large range of energies and still be within the same band. There are energy amounts which are forbidden for the electrons, but it is a very different situation from the highly limited energy levels of the isolated atoms' electrons. As these energy bands are created by the collective grouping of solids atoms, the bands are attributed to the semiconductor as a whole rather than to individual atoms. There is an energy level called the valence band, and electrons within this amount of energy remains tied to atoms and do not form part of any electric current. Those that gain energy to jump up to the conduction band become delocalized and can move through the semiconductor as part of a current as well. Now there is an energy level called valence band. ये होते हैं, they are not part of the current. But the ones that gain enough energy and become part of the conduction band, they can move as a part of the current. Got it?
Right.
अब ये जैसे ये वाला इलेक्ट्रॉन हम कह लेते हैं this is a part of a valence band. If it
Mm-hmm.
gains energy, let's say
He
due
will
to
be
the
able to
EMF supply,
conduct
it's gonna jump
electricity.
to the conduction band, and this one will be a part of the electric current. Got it?
Right.
Good. So here we can see we have shown the valence band and almost a full conduction band and all of that. Now the number of delocalized electrons in a semiconductor is low compared with metals, and so the current they will carry is therefore lower than metals, but for the same applied voltage as well. At higher temperatures, they have more conduction electrons as more electrons are elevated into the conduction band, and there will be a temperature related reduction in current due to the increased collisions with fixed atoms. But the increase in available conduction electrons is a much bigger effect, and overall, a semiconductor will carry more current as the temperature goes up. Its resistivity effectively drops as the temperature rises. So when an electron enters the conduction band and moves away, this leaves the atom with a positive charge, and the empty space the electron has left is referred to as a positive hole. If an electron from another atom moves to fill the hole, leaving its original atom with a hole, the hole has then moved, and as the electrons will be attracted to jump in the positive direction of the applied voltage, the hole will slowly appear to move in the opposite direction. A positive hole moving towards the negative cathode is like another charge carrier adding to the current flow in a semiconductor, and it is like the current flow in electrolysis, where the positive move towards the cathode, negative moves towards the anode.
Mm.
अब होता क्या, when electron conduction band में enter होता है, it becomes part of the electric current. ठीक है, और वो जब एक
Right.
वैलेंस बैंड को लीव करता है वहां पे it leaves an empty hole. अब
Okay, right.
ये वाला जो एम्प्टी होल था, यहाँ से इलेक्ट्रॉन निकल गया, another electron comes in place to fill this empty hole as well, और ये वाला अगले होल पे जाएगा, तो ये कीप दे फिलिंग द ईच एंड एवरी होल, और ये एक दूसरे से एक होल से दूसरे होल में जंप करते जाते हैं. दिस इज हाउ द electrons or the current is transferred. Got it?
Yeah, right.
A diode is made by joining different types of semiconductor, which normally creates an energy barrier at the junction between them. This blocks the movement of charge carriers across the barrier, and this barrier can be overcome in the forward direction if a small forward voltage is applied. अब diode क्या होता है? Diode is a component that ensures the current's one directional flow, that the current only flows in one direction. एंड दिस डायोड इज ऑल्सो मेड ऑफ मैनी सेमीकंडक्टर्स जो कि जंक्शंस फिल करते रहते हैं ऑलरेडी, दे डोंट वांट कि एक दूसरी डायरेक्शन के अंदर इलेक्ट्रॉन्स जाए, तो ये ऑटोमेटिकली वो जंक्शंस फिल रखते हैं. इन द रिवर्स डायरेक्शन ओनली अ वेरी फ्यू चार्ज कैरियर्स कैन पास थ्रू एट लो voltages and they account for a tiny leakage current. Once the reverse voltage becomes large enough, it can overcome the large reverse energy barrier and force the conduction process in the opposite direction. So here you can see the diode is a forward bias diode as well. LDRs जो होते हैं, लाइट डिपेंडेंट रेजिस्टर्स, वी नो कि जब इनके ऊपर लाइट इंक्रीज करेगी, रेजिस्टेंस इज गोइंग टू इंक्रीज. Light dependent resistors have a property that their resistance depends on the light level around them. In brighter conditions, LDR will have a lower resistance. And LDRs are made from semiconductor material as well. कि जैसी light land करेगी, it's gonna boost the electrons from valence band up to the conduction band. क्योंकि जब light increase करेगी, resistance कम होगी and the current is going to increase. क्योंकि अब less resistance है. तो जो इलेक्ट्रॉन होगा दैट इज गोइंग टू गेट एक्साइटेड फ्रॉम द वैलेंस बैंड एंड जंप अप टू द conduction band. Got it?
Right.
This makes the LDR to conduct better, to conduct more electricity, to conduct more current because now it has a lower resistance.
L
इसलिए
yeah.
LDR कैसे काम करते हैं? Brighter the light, lower the resistance,
Lower the resistance, higher the
electron
current.
moves from the valence to conduction band. It makes the LDR a better conductor of current and current increases as well. थर्मिस्टर्स वर्क इन एग्जैक्टली द सेम वे. थर्मिस्टर्स क्या करते हैं, जब टेम्परेचर इंक्रीज करेगा, अगेन रेजिस्टेंस वुड डिक्रीज विच मीन्स करंट वुड इंक्रीज. अब इसकी भी एक्सप्लेनेशन सेम होगी. व्हेन टेम्परेचर इंक्रीजेज, व्हाट हैपन्स, द energy increases and the electron gets energetic to leave the valence band and moves to the conduction band. Because the resistance has decreased, now more electrons are there in conduction band, current would increase again. Because thermistors work in exactly the same way except that their resistance depends on thermal energy from the surroundings. The most
Right.
common type of thermistors are referred to as the negative temperature coefficient thermistors, which use thermal energy to boost their electrons into the conduction energy band, meaning that their resistance would fall as the temperature would rise. So can you tell me what are insulators?
Insulators which cannot conduct electricity were bad, very bad conductors, such as non-metals, plastics, and
Mhm.
such.
Electrical insulators can be thought of as materials in which the energy gap between the valence band and the conduction band is so large that there are virtually zero electrons available for conduction. Conductors में क्या होता है, जो distance between valence and conduction band होता है, it's very small, easily
Mhm.
jump हो जाएगा अगर आपने एक एनर्जी
And they have
दी.
D localized electrons.
यस, अब इंसुलेटर्स में वैलेंस और कंडक्शन बैंड में इतना लार्ज डिस्टेंस है दैट द इलेक्ट्रॉन्स कांट बी इवन एक्साइटेड इनफ. हाउ मच इलेक्ट्रिसिटी और हाउ मच करंट आर यू गोइंग टू पास टू द इंसुलेटर्स? You can't,
Mhm.
because there's such a large distance between the valence band and the conduction band that no electron can even reach the conduction band as well,
Conducting band.
which will be therefore be no conduction holes either as well. And a very large input of energy is required to make the material conduct. अगर आप एक piece of wood लोगे, wood doesn't conduct electricity. कितने
Mhm.
volts, thousands of volts of जब आप energy pass करोगे in wood, then maybe you might feel a bit of a charge or something or electric shock. लेकिन
You
insulators
probably
में,
burned by then.
yes exactly, तब तक तो वो इतना एकदम हो जाएगा. We can't say, ये नहीं है कि valence और conduction band exist ही नहीं करते, they do exist.
Yeah.
कंडक्शन बैंड्स एंड वैलेंस बैंड आपके पास एग्जिस्ट करते हैं कंडक्टर्स में भी एज वेल, इंसुलेटर्स में भी एज वेल. बट इन इंसुलेटर्स दे हैव सच अ लार्ज डिस्टेंस और गैप बिटवीन देम कि यू हैव टू गिव वेरी 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 हाई इलेक्ट्रिक करंट in order to make the electron excited to the conduction band. But once it
Mhm.
is, it results in melting, damage, or it can break as well, it can burn as well, like you just said as well. For example, glass is normally an excellent electrical insulator, but at a very high electrical field, maybe even 10 billion volts per meter, it can act as a conductor. Got it?
Right. Yeah.
Superconductivity. Resistance increases with higher temperatures because the higher level of internal energy in the material causes more vibration of the fixed ions. These ions collide more often with charge carriers to reduce their speed of movement through the material. Reducing the temperature, therefore reducing the resistance, allows the greater current flow as well. Now, cooling to even lower temperatures continues this trend until something quite unexpected happens, and below a certain critical temperature, the resistance suddenly drops to zero. This is called superconductivity, where the critical temperature varies with material, but for most metals it will be below minus 243 as well. कि बहुत लो टेम्परेचर्स पे समथिंग अनएक्सपेक्टेड माइट हैपन और आपका रेजिस्टेंस बिल्कुल जीरो हो जाती है और करंट मैक्सिमम हो जाएगा, वी कॉल इट सुपर कंडक्टिविटी। अब ये क्रिटिकल
Right.
टेम्परेचर हर मटेरियल का डिफरेंट है, सम ऑफ देम हैव माइनस 243, सम ऑफ देम माइट हैव 135, some of them might have minus 300. So these superconductors are especially useful in applications where a large current is needed, as a large current would normally waste too much energy or damage the surroundings as well with the heat dissipated. For example, strong magnets होंगे जैसे डीसी मोटर्स, एसी मोटर्स या ट्रांसफॉर्मर्स के अंदर यहाँ पे पार्टिकल एक्सेलरेटर है, उनका सुपर कंडक्टिंग होना बहुत ज़रूरी है। सो यू कैन कूल देम टू वेरी लो टेम्परेचर्स बिकॉज कूलिंग देम makes it super conductive. Got it?
Right.
Good.
But do all they have same temperature? All metals will have same temperature
No,
for
it varies.
superconducting.
It varies.
Okay.
So semiconductors are materials with a lower resistivity than insulators but higher than conductors. They usually have small numbers of delocalized electrons that are free to conduct. Valence band is a range of energy amounts that electron in a solid material can have, which keeps them close to one particular atom. Conduction band is a range of energy amounts that electrons in a solid material can have, which delocalizes them to move more freely through the solid. Critical temperature is the temperature below which a material's resistivity instantly drops to zero. And superconductivity is the electrical property of a material having zero resistivity and maximum current. Got it?
Right.
Good. And that is the end of your topic number 4A.